Now, the obvious question is similar to uh, the sorting algorithms that we apply in the in-memory data. That is, in-memory means when we are applying the sorting algorithm when the data is stored in the primary memory, that is in RAM. Can we apply a similar algorithm when the data is stored in the disk or in the secondary memory? The answer is no. Why? Because if we store, so as we have seen, this entire list of say 100 million tokens, if we somehow store them in the disk and if we apply, so basically if we store them from the RAM, if we store them in the hard disk, and if we apply this same algorithm, why this will not be effective or it would be taking very long time? Because as we have discussed, all the computation needs to be done when the data is in the RAM. We cannot actually perform some operation when the data is actually in the hard disk. So note that, let me give you some analogy with our regular handling of computer in this regard as well. So let's consider we are playing a video which is stored in the hard disk, right? So what actually happens? So I hope all of you are using this software called VLC. Using VLC, if we start playing a file, say 1.mp4, a part of it, so basically a video is basically a stream. The first part, so first 10 seconds or 20 seconds based on your operating system, your processor as well as your free memory, some portion of it will be basically bring to the RAM. Basically they will be brought into this RAM, some place in the RAM. And then it will be, I mean, after they are gone, I mean, after they are played, VLC will be responsible to basically remove them from the RAM and take the next, say, 10 seconds or 1 minute into the RAM again. So every time we are handling anything, the data should be in the RAM. So that's why if the computer is already overloaded and if you start playing a video, you will be noticing that it is taking some time. And during that time, what it is actually doing? It is basically swapping some, basically swapping out some memory, some information from this RAM into the swap space that we have discussed in the last class. And it is freeing some memory, and considering that memory, it is basically using to store the new, this say 10 seconds or 1 minute information, the stream. So again, back to the actual discussion that we were having. To sort this record, we need to have the entire information. I mean, not the entire information, but the part we are storing, we need to have that in the RAM. And we cannot actually apply them, because the way to apply them, we will be able to apply them. What we will be doing in that case, basically we will be taking 2 items at a time and we will be sorting them. Like in case there are say 6 items. So for the sake of this discussion, let's consider that there are 6 items that we want to sort and they cannot fit inside the RAM altogether. So what we will be doing is we will be bringing 2 at a time into the memory and we will be sorting them, like sorting in the sense, I mean, we can also basically sort in some way and merge them together. We can actually sort them and merge them together. We can also sort them and merge them together. Then we are from 6, we are ending up with 3, which can again be, so basically we will be bringing this from the hard disk into the RAM, bringing this from the hard disk into the RAM, and then the sorted result, which is this, will be again written back to hard disk. Then RAM, then again result will be this, which will be again written back to hard disk, then again back to hard disk, then again we will be bringing these two into the RAM, sorting and merging, then we will be taking this, and finally we will be sorting and merging them together. But as I said, it will be too slow. The reason is it is actually involving many disk seeks. Now as we can see, I have highlighted, or made this italicized. So why? So it is actually a very important concept. So disk seeking, or the seek time of a disk, is basically the time it take to bring certain information that is stored in hard disk into RAM. This is the time that is called seek time. So this is basically the disk seek time. So these are some concepts from operating system, but I am trying to give you a very brief overview of this whenever I am encountering them. So of course we need some other type of algorithm which can be applied on the disk. So in general, they are actually called external sorting. So there are broadly two ways, or two broad algorithms. First is called block sort based indexing or sorting, and second is single pass in memory indexing or sorting. So in the block sort based indexing, we will be calling this function with all the documents basically. So while all the documents are not processed, we will be creating individual blocks. So here n is the number of basically the nth block. So we are initializing that to 0. Now we are incrementing it. Now the value of n is basically, at first it is 1. So basically now we will be reading a block of data from the hard disk into the memory, into the primary memory, into the RAM, and we will be basically performing that tokenization, linguistic processing and all, and making the things like the list and the sorted list in this BSBI invert function, using this function. So this function is basically responsible for sorting and merging, basically the sorting the individual lists, right? So this part is basically responsible for the tokenization and linguistic processing, and this is basically sorting the list. And the block of data will be written back to hard disk. So from the hard disk, we will be reading the data, the raw data. So if this is the hard disk, we will be reading the data. So let's say this is the raw data, say D. We will be reading it into RAM and do this, and this the sorted list will be written back into the hard disk as, say, D prime. Now this is basically the list. This was the raw data. So basically this is D, and what we are storing back in the hard disk is basically a list containing the token doc ID pair. Now in a block there can be multiple documents, so that's why reading a block from the hard disk will be actually reading multiple documents altogether. So in sum, we will be reading multiple documents altogether into the memory RAM. We will be basically tokenizing them. We will be applying those linguistic processors. Finally, we will be getting this turn doc ID pair. We will be sorting them, and we will be write back the result into again the hard disk. So we will be performing this one after the other for each block, and finally we will be merging the individual blocks that are stored in the hard disk. So in the hard disk, after line 6, in the hard disk we will be ending up with multiple blocks. This is one block, this is another block. Individually, they are all sorted. Finally, we need to write another function which is merge block, which is basically will be taking the individual blocks and they will be basically sorting them to make a large block. And that will be again written back to the hard disk. In the second type of, so of course, one question that you might be having is how to write this merge blocks function. I'll be leaving it to you to think this a little bit. Later on, we can discuss. The second type is single pass in-memory indexing. Here, after reading a document, I will be basically tokenizing it, and I'll be passing the stream of tokens into this function as a parameter, right? And what we'll be doing is we'll be basically making a dictionary, a new hash, basically a new dictionary has been created. Now, until and unless the memory is free, memory is full in the RAM, this is basically RAM memory. So while free memory is available in the RAM, we will be taking the next token in the stream. So basically, this is basically a list or basically a stream similar to the video stream that I have talked a couple of minutes back. So basically, I'll be basically reading the individual words as tokens or as token streams in this function. And while there are free space in the memory, I'll be basically taking that term. If the term is not already, so I'll also be keeping one dictionary, which is basically a key value pair, as I hope you can remember, which is basically a hash map, hash table. So if the term is already in the dictionary, so I will be basically getting its posting. So let's go line by line. So if the term is not in the dictionary, in the beginning the term will not be in the dictionary because the dictionary is empty, like we are initializing the dictionary. If it is not in the dictionary, I'll be adding the corresponding token into the dictionary with the corresponding posting list. And finally, that posting list here with the corresponding token or basically the term along with the doc ID will be added to the posting list function or basically the large posting list associated with this token. Now, if the term is already there in this dictionary, if it is already there, what I'll be doing is I'll be getting its existing posting list and I'll be adding again. So as you can see, this statement, this line number 10 statement is common even if the term is present in the dictionary already or not present. So if it is already present, I will be adding, basically getting the existing posting list and I'll be adding the new posting list or basically the new doc ID into this existing posting list. So if the term is say T is already present say in the 1th document, from this statement I will be getting this, and from after 7, from 10 I will be basically, so again let's say I have encountered T in document 2, right? So this is basically the token. So this token is consisting of two parts. One is basically the term of the token and second is basically the doc ID of the token, right? If the term is already present, I'll be adding the doc ID into the existing posting list. And if the posting list is full, there is no memory left in the posting list or memory left in the memory, in the primary memory, what we will be doing is we will be basically, or not actually in the primary memory, but so basically posting list is a list. So you can consider it as an array. So if array is full, we'll be basically doubling the posting list. Basically, we can use the realloc function to double the size, right? So for the entire token stream, after the traversing the entire token stream list of tokens, we'll be sorting the dictionary, and we will be writing them back to the disk. Note that it is while the free memory is available. At any point, if the free memory is not available, we'll be again doing this operation because this is outside. So basically, you can see this is outside the while loop. So while loop is starting from here, it is ending here. So if the memory is not basically full, I'll be sorting the existing dictionary and I'll be basically writing that dictionary inside the inside the hard disk, and I'll be returning the output file. So basically the file where I have written the block or written the dictionary. So again, similar to the block sort based indexing, we will be ending up with a list of blocks which are individually sorted, and we need to perform a similar operation like a merge block here as well. We need to perform the merging operation here as well. Okay, so again, taking a step backward, for the indexing process, this, given a stream of data like a set of documents, our primary target of indexing is to make a list of terms from the document and to store the documents in which this term is actually occurring in. So this is basically the terms together with the document frequency and the doc IDs in which they are actually appearing in. Now, while doing the retrieval, what we will be doing? Let's say we are encountering with, the system received the query Brutus Calpurnia, 2 terms. Now note that this list, this is basically a list, isn't it? This list is actually sorted. This is a dictionary that we have made as in the fashion of in sorted order. Why sorted? Because we want to perform an advanced search on this. An advanced search, of course, the basic searching is linear search. It would be taking a huge time, significant time. But if it is sorted, we can actually apply binary search. So for that, this is sorted. So for the 2 terms, Brutus and Calpurnia, after applying the same linguistic processing, which will be transforming Brutus and Calpurnia to the same form. Here in this example, I'm not actually tokenizing or basically not applying any linguistic processor here, like they are kept as it is. So basically we need to apply the same linguistic processing module here as well for the query. Now we need to get the posting list associated with the individual query terms, and we need to get the corresponding posting list, and we need to perform a merging in case the query is of type AND. If it is OR type, then basically the union of these 2 lists should be considered, as we have discussed earlier. But as I hope you can understand, we are still in binary retrieval. That is, we have no idea which of them are basically more relevant than the other, because we are only considering whether, while making this posting lists, all this either BSBI indexing or SPI MI indexing, we are not considering the frequency of the term. That's why we are still the binary retrieval. So why we are actually stuck with binary retrieval? Because we are only recording the presence or absence of a term. The presence is indicated by a 1 and absence is basically 0, which is basically similar to the incidence vector or in the term incidence matrix that we have made earlier. So there is no notion of term importance, as we have discussed. So all the presence of all the terms are considered equally important, which is not actually true. So how can we actually overcome this situation? So this was the ultimate thing that we will be indexing, which is basically the inverted list or inverted index. So if I zoom this part, if I zoom into this part, this looks like this. So here we are storing term, the term itself, T, the document frequency of the term, Note that this was stored to make this skip list, and there are so many other operations that we have discussed. And this is basically the doc IDs, right? But we don't know how many times the term Brutus is present in this doc ID or in this document. That's why we are only considering whether it is present or absent. It might be the case that Brutus is present in this document, say 10 times, and in this document, say 2 times, and in this document, say 143 times. We know with our human intelligence, we know that this seems to be more relevant for Brutus as compared to this. But from this posting lists, we have no way to distinguish that this is much more important than this one, because we are only storing the presence or absence. That's why we are ending up with a Boolean retrieval still. Now, I guess you can understand how to overcome this situation. So basically, together, together with this doc ID, we will be storing the count, basically the term frequency with which the individual term is occurring in this document. For example, Brutus is present in this doc ID 1 with term frequency 1. So this is basically the term frequency, TF in short. Brutus is present in 1 with term frequency 1. That means Brutus is present only once in first document, 3 times in second document, 2 times in fourth document, 21 times in 11th document, and so on, similar to the other terms. So earlier we were storing only the doc IDs. That's why there are no way to distinguish between whether a document is more relevant to a term or not. But if we store the term frequency, we can actually get that extra information that will be needed to actually get the ranked based retrieval from the Boolean retrieval. So in the posting list, what we will be storing? Basically, pardon. So this should be not the term. So basically, for the term, we will be storing the doc ID. Doc ID. The term frequency of that document, of that term in that document. Together with that, sometimes we also store another information, which is called position of the term in the document. Like if we consider a document like this, say this is the first word, this is the second word, this is the third word, and so on. A third information sometimes we also store, which is called the position of the term. Let's say if the 17th term is say say united. So 17th term, 29th term, and say 43rd term are united. So what we will be doing, sir, this is say doc ID 1. So for united, this will be in the dictionary. We will be storing D1, comma 3, because it is present 3 times for this united, comma the places at which they are actually occurring. So basically we can consider a tuple, say 17, 29 and 43. Note that in the third field, so there are 3 fields now. Earlier we started with only one field, only the doc ID. Then we incorporated another field, which is the term frequency of that term in that doc ID. Now we can also store another information, basically the places at which they are occurring in this document, starting with an offset of 0, say. So we are starting with the 0th term. 17, here 17 means this united term is present in this 18th location in this document D1. So the length of this will be equal to the term frequency. I hope you can understand this. So this information, this extra information sometimes will be important when proximity based search are applied. All right, so just to give you the recap of today's discussion, while making the inverted index, we need to store two things: a dictionary containing all the terms, a posting list, for which is basically a list for all terms, for each of the terms in the dictionary containing the doc IDs in which it is appearing. So we have discussed that together with only the doc ID, we can also store the term frequency as well as the position of the term in the document as well. So for this course, we will not be using this much, but we will be mostly focusing on these two, because this is the most important information using which the retrieval models will be working on. But again, one question still remain unanswered is how to actually, while retrieval, how to actually look up this dictionary, because this dictionary can also be quite large. As we have seen, it can be, I mean, considering, so this is the length of this is will be basically the number of unique terms, right? So fairly large collection can have, say, more than, say, 300,000 unique terms, more than 300,000 unique terms. So there will be 300,000 different, I mean, rows for this. So to do the retrieval, we need to keep everything in the memory. Again, it is actually a little bit problematic. So we will be discussing this later on, how to keep these things efficiently in the memory to do an efficient retrieval. Okay, so the terminologies that we have encountered so far, first is C, basically specifying a corpus or a collection, which is basically a set of documents. D, this is basically a textual indexing unit. So basically C is a set of D, D1, D2, and so on. And each of these document is consisting of multiple terms. So basically each DI is basically a set of T, T1, T2. Note that we will be referring to the same concept as tokens, terms, words interchangeably in this course. And while referring to them mathematically, we will be using the notation W. Document frequency is basically the number of documents containing the term W. Term frequency WD, which is basically the count of W in the document D. And collection frequency, which is basically the count of W in the entire collection C. Right? And for each query, we will be referring to them with a queue containing multiple terms Q1, Q2 up to Qk. That's it for today's class. So this is basically just to give you a recap of different terminologies that we will be using, we'll be referring to later on.